Hello, welcome to Burning Questions. For the keen observers, you'll notice that Glenn isn't with me today, but thankfully I've been joined by Darryl Wells, who heads Quailfire's research and development team, and he's going to be helping me talk through some questions regarding fire resistance testing for service penetration. So thanks for joining us on this episode, Darryl. Just in case anyone doesn't know, if you just wanted to sort of like briefly introduce yourself and sort of what sort of testing you've done, might be a little bit useful for the audience. So.
Good, yeah, I'm Darryl. Thanks, Alec. I head up the R&D. Obviously, development for us is a big thing.
Definitely.
So we take feedback from our customers and we create solutions for the challenges and problems that they come up with. So yeah, we work closely, don't we, Alec?
Yeah.
Obviously, Alec's on the front face talking to customers with the technical, and obviously feeds back a lot of information to me.
Yeah.
Which is really helpful in us innovating and creating solutions for the future.
Yeah, very good. Yeah, it's been really good. Like I said, for all the customers that are already with Quailfire, you've probably seen this firsthand, how we might not have a solution, but you come back to us in the future, and Darryl and his team have managed to find something and get the test evidence out there. The testing that we do, we mentioned on another episode, is more towards service penetrations and linear gaps. They're tested to the BS EN 1366 Part 3 standard for service penetrations, and then it's the BS EN 1366 Part 4 to the linear gap seals. So just again for the audience, we mentioned this quite a lot in our videos, Darryl. When I mention BS EN 1366, what is that as such? It's like a guideline, and it's like a tool. What do you use it for?
Sure, yeah. So it's a test standard which is being created, and it lays out in there, like you say, the rules for testing specimens, etc., and how you can then get a scope of application off the back of that, so that what you test can be extended into multiple applications that happen on site, basically.
Yeah. So it's scope of applications. Both those standards I mentioned before have actually had recent updates, so they actually have increased the scope of application, which was, like I said, mentioned in a previous video, warmly received. So we're now at I think both are 2021, I believe, is it?
That's right, yeah.
Yeah. So that had a greater scope of applications. So we are going to look into some of the things that we have to do when we do fire testings, but one of the questions we're getting a lot in the technical team at the moment, so I thought I'd answer it earlier on, is the BSEN 1366 Part 3 test standard, for example, was 2009, and it was updated just at the end of 2021, so it's now 2021. This has sort of freaked out the industry, and they're thinking that anything that was tested prior to the 2021 is now invalid. That's not the case. Okay, it doesn't supersede it. It's just an update. So any testing that's been done to the 2009 or the 2021 is still used by accredited test labs like UL or Warrington Fire. They're just two that we use. They still use all that evidence, and provided nothing that was tested to 2009 it goes against what's in the update, then it's still valid and still used. So when it comes to looking at our products, for example, what you want to be looking at is the classification, the ETAs, because that's the field of application, not necessarily what the test standard as such has been tested to. So I thought I'd get that out early. But one of the things we're going to look at first, Darryl, if that's okay, is when you go to, say, the test lab and you're doing a test, with service penetration, what's the test lab looking for as such?
Yeah, so there's two criteria, isn't there? There's integrity and insulation.
Yep.
I think you've probably covered it off in some of your other technical
a little bit, yeah.
Integrity is basically the passage of fire, and so there should be no sustained flaming on the specimen, and there should be no gap, and the two. Well, there's obviously visual assessment during the test to check there's no sustained flaming, check that the integrity hasn't been compromised, and also they use a couple of pieces of equipment, one being the cotton pad.
Yep.
So I've got a cotton pad test video to just show you here. So what you can see here is the cotton pad test. It's basically a stick with a little cage on the end with a piece of cotton wool, which is kept in dry conditions. It's placed against the specimen where they can see any small gaps, any glowing, like you can see here. And the idea is they put it against it, and if that cotton wool ignites within 30 seconds, that's deemed as an integrity failure. So another check they do for integrity during the test is if there is a gap that forms, so like a gap of visibly more than 25 mil or more, they have a probe similar to the cotton wool rod where it has a steel 25 mil end to it, and they will try and put that through the gap. If it does penetrate through the specimen, that's deemed as an integrity failure because the gap is larger than 25 mil. So that covers off integrity. The insulation value is the other criteria, isn't it?
Yeah.
Alex? So that is basically checking the temperature rise of any part on the specimen from the ambient temperature. So it's 180 degrees above the ambient temperature of the lab at the time. If the temperature of the thermocouples which are on the specimen rise over this, that is deemed as an insulation failure.
One of the things that comes up actually from technical is people sometimes get a bit confused that a specimen might have a different rating for integrity and a different rating for insulation. So it's kind of just probably understanding why that is. So, I mean, you mentioned there during the test, they're doing the visual check for integrity, they're doing the probes, the cotton pad, whereas the insulation, that's done by, in the video Darryl showed, you saw the little cables, they're connected to the thermocouples, and it's that sort of reading is not taken to after the test is finished in it. So it might be that we could get 2 hours integrity, but you might have only got 60 minutes insulation because of the heat transfer. So that's sometimes why you'll see a different rating, especially with non-combustible materials, with metal like cable trays or uninsulated pipes.
Particularly copper.
Yeah, copper.
You get a lot of heat transfer. Yeah.
So that's the reason why on our drawings, for example, you may see E120, EI60. The specimen was still tested at the same time, but it's just got a different reading for the integrity because that's what we check on the day, and then insulation is recorded, and that's what takes a little bit of time with the test reports.
Just while we're talking about that, I guess Alec, it might be good to cover off the local interrupted.
Yes, the different insulation.
So where we have steel or copper pipes, typically to increase the insulation value.
Yeah.
During a test, we will have the detail might include a foil face rock fibre, which it says on the drawing, say locally interrupted, but that means that it's not continuous. The insulation isn't continuous through the specimen, but we wrap the service in this rock fibre, foil face rock fibre, to prevent the heat transfer, and then therefore that upgrades the fire rating the insulation fire rating to a greater rating than if it was exposed copper or steel, for example.
Yeah. Prime examples that, like our cable tray detail. You've done the same detail with HPE without rock fibre. E for a cable tray is E120 for integrity, EI60, but when you did the test for the rock fibre, they both got 2 hours fire rating. So yeah,
EI120. So that's typically what we do. In terms of other types of insulation, we have obviously got a lot of data for continuous and sustained insulation. Is the technical term for it. So it's that's where you have a pipe which is fully insulated, and the insulation continues through the separating wall or floor. And then typically we obviously have got a number of solutions, but we've got Quell Coil, our intumescent wrap, which is used around the continuous insulation, which then closes off the insulation in the event of a fire. There's a couple of options.
It should be up on the screen now, but there'll be a table just showing you the different sort of insulation types around pipes and the different terms. You'll see letters on a drawing like CS, that's continuous sustained, LS or LI, and this table, but if you need more information, we'll just speak to technical and we can get that sent out. So that was good, sort of covering that aspect. So I suppose actually another thing that people might not be aware of then, what sort of furnaces are there sort of these accredited test labs that you use, and what's the differences between them?
Yeah, so in simple terms, I guess, you have what you call an indicative furnace, typically, which is a small scale furnace, typically 1.5 metres by 1.5 metres, either a floor or a wall. Typically they're a cube furnace, so they're a furnace which has a wall and a floor of that size. And then you have full scale testing where you've got walls which you can test flexible walls in plasterboard partitions which are minimum 3 metres high. There are some laboratories out there with larger furnaces even as big as 5 metres by 4 metres in size. And then there's obviously the full scale floors as well, which are used primarily for load bearing floors and testing steel, structural steel, etc., which are again on the larger size of 4 metres by 3 metres in area. So yeah, that's a couple of, indicative furnaces are typically used for R&D purposes, but you can also, for service penetrations, use those furnaces for solid floors and for rigid walls too. So
yeah, perfect. But you said you might have a video that you can show of a furnace. Do you reckon we can sort of show them one just so the audience? So let's have a look at that now.
So you can see here, this is an indicative furnace, small scale of 1.5 metre by 1.5 metre wall, this is after the end of a 4-hour test. They're taking the furnace off, so you can see it's actually 4.5 hours I think this was. So this is you see how hot it is. This here is an example of a full scale wall test, 3 metre by 3 metre, and so this is at the end of a successful 2.25 hour test, and they're removing, obviously you can see the failures which occurred after the 2 hours on the non-fire side, but you can see now in the fire side, so that's inside the furnace there. You can see the furnace jets there on the side and they pump gas in.
So what sort of temperature is normally inside that?
At that stage in a fire you're talking well over 1,000 degrees, probably getting on for 1,200 degrees.
It's very different from the inside to the outside, as you can see. So it's good to see that in real life. So that was, thanks for sharing those videos, Darryl. That was just a quick one of the small indicative and the full scale wall test. They're primarily the furnaces that we use. Darryl did mention obviously there's a full scale floor test, but that's more when you're worried about the load bearing aspect as well as the integrity and insulation. So yeah, one of the other things I thought might be very beneficial for our viewers is sort of understanding sort of the interchangeability of supporting constructions. So what I mean by that is when you look at our detailed drawings, you'll see that our drawings always depict a wall in a certain way. It shows, you'll notice it, that the insulation is cut back, it might not be a framed and lined aperture, etc., etc. It has a specific drawing, and the reason why we do this is because that, and I'll let Darryl explain more, is there is a way of testing the worst case scenario, I think it is, and then that would cover a number of different walls. Am I correct?
Yeah, that's right. So like you say, we test typically with the insulation cut back. The reason for this is what we have here on the screen. So what you can see is the construction tested on the left here. So this is the insulation in the wall cut back, 100mm from the specimen you test. And that then covers for a number of other wall types basically. So it covers for uninsulated and insulated walls, and it covers for thicker wall constructions too. So that's the reasoning behind it, but it is a worst case scenario typically.
Yes.
So we have done some other larger seal sizes, for example, with larger apertures, but they have to be framed and lined. As per the wall manufacturer's instructions.
And all this information is on our detailed drawings, so make sure you read them carefully. So that's just one of the sort of scope of application rules in the BSEN standard. One of the things that obviously working with you I found quite interesting is sort of there's approaches, especially when it comes to say plastic pipes, but it can with other pipes as well, is sort of you have the critical pipe method. That's just one thing, and obviously also we can look at sort of the cluster method and spacings. But looking at the critical pipe, why do we do that as an approach? What's the reasoning behind the critical pipe aspect?
Sure. So in simple terms, we test a wide number of different pipe types. You've got PVC, polyethylene, polypropylene. There's so many different types of pipe out there. And we test a wide variety with our closure devices, so maybe our collar or our wrap, etc. Once we've done our base testing on a number of pipe types, that then allows us to take all that data, and you pick basically with your certification body the most critical performing, so effectively the worst performing pipes of all of them. And we then can test 3 pipes in various other applications, so in back seals or different wall constructions or floor constructions, and we can then get an extended scope application for all those other pipe types that we previously tested. So that's typically it.
That's good.
Obviously, like you say, what you test is what you get, but when you start looking at extended scope of application, you can use this approach to make it feasible to test other applications, but not have to test your other 40, 50, 60 odd pipes.
Hundreds of pipes. So which is why then obviously for us and for our customers, it's why it's more important that they review, say, the classification report, because that's where the accredited test lab has given that field of application, which covers the wide range of pipes that you did in the initial test, the wall thicknesses as such. So that's what's more important than, say, the test report as such, because that's the baseline for the accredited test lab more than the customer as such. Thanks, Darryl. That was really fascinating. I found the critical thing quite interesting. Hopefully the viewers do as well. One of the other things I think is really important is spacing. There's a lot of confusion. I spend most of my day in the technical team talking to customers about the spacing, so I thought it might be good to sort of look at how we have to test that. So I mean, typically when you do initial testing, you have a certain spacing that you need between surfaces. That's right, don't it? It's typically what, 200 mil, I think it is it?
Yeah, that's right. Obviously you test your individual specimens generally with a 200 mil, so that the if you get a premature failure of one specimen, it doesn't affect the other.
Okay.
But that's what you do for your initial single service penetration.
Okay.
But then you extend and go on to test further. You might take the critical pipe approach of what you've tested already, and you test it then in a cluster form, which is what you were referring to. So you see on the screen now, this is cluster formation, which is set out in the test standard, typically in this triangle form, and it's basically testing the proximity of other surfaces
around each other.
Around each other.
So with that as well, I mean, obviously there's different scenarios that I know you've tested. So like the picture there, is that a wrap around the pipes? What's fire stop seal? So you've got a fire stop seal around each of those pipes, or just around the collective? You can do it alternatively, can't you? You've done some scenarios where, say, HP is around very small pipes as a bundle, but this one is more, you could have individual, and it will be depicted on the test report, classification report, and that side of thing, won't it?
Yeah, that's right. So you're testing the proximity of the closure device to the proximity of another closure device on another service. So it's again, it's a, you can test the worst case scenario, for example, testing zero distance between the two closure devices, to prove that the services can be installed that close.
Yeah, no, it's very interesting. But I suppose from your picture there, and one of the things I think is quite good for our audience to sort of realise is the practicality of it as well. I mean, even when I know you've done big tests where you had loads of surfaces close together. I mean, that was quite hard for you and your team to install on site. The conditions going to be sometimes a lot worse. The pipes don't finish 500 mil from the edge, so that, for the people out there, just because we do 0 mil, they should still think about the practicality of the install and try and leave some space for the fire stopper, shouldn't they?
Absolutely, yeah. And that's the ultimate, it's got to be realistic.
One of the other things that I thought was very useful, especially for people out there, is understanding cables and cable carriers, because some might not know that there is actually a specific cable configuration that you have to stick to. And I just thought you might want to share what you have to do to get, cables, cable bundles, ladders, trays, what you actually have to do to get that tested.
Sure, yeah, so there is, it sets it out in the test standard, what you can test to get a certain scope. So we generally test the full cable configuration, it's called. So it's got a number of different types and sizes of cables, which cover basically up to 80 mil cable.
Yep.
But this set, which I'm going to bring up here now, is actually covering for ladders, cable bundles, trays. You can see the photo there with what that looks like in real life, the drawing and the actual photo of a test setup. And then this is agreed in the test standard that if you test this set, it covers then for the scope of application that is typically in our detailed drawings and in our classification report.
Yep. Yeah, very good. But again, also sort of tying back to what you mentioned earlier with that, this is sort of a big application where integrity is kind of determined on the day, but it's insulation because a lot of those different parts of that cable configuration can transfer heat a lot quicker than others, so you might get a different rating for the larger cables to the smaller cables, the cable carriers. So that's where it gets a bit more complex, doesn't it?
Yeah, that's right. So on the whole set, the standard sets out where the thermocouples should be measuring the reading during a test, and the cable configurator is literally plastered in thermocouples, pretty much monitoring the reading of the temperature during the test, and then obviously you review that data afterwards in the test report, which gives the temperatures, and then you can work out the insulation failure point if it does, and obviously the certification body that then uses that data to then give the scope of application for the EI rating.
Yeah, thank you. And that kind of ties very well into my last question, sort of limitations when it comes to fire testing.
Yeah, so in terms of the test standard, it sets out a lot of scope, obviously, but we're in a big world where there's all sorts of other applications which aren't covered off in the test standard, and therefore sometimes we do have to do ad hoc testing to get something rather than nothing.
Yeah.
But that obviously does come at a cost anyway. These fire tests can cost anything in the region from £10,000 to £20,000 and more in some cases.
Yeah. And that's just for the test. That's not including the paperwork.
Absolutely. Yeah. Oh, yeah. They like to charge you for that as well.
Yeah, definitely. And talking about that sort of paperwork. So, I mean, sort of time frame, because I know everyone would ring up and say, I want this tested. Sort of when you look to average, some of them are much longer, some are much shorter. But when we're talking about service penetration, what would you sort of say is the average time frame? If you're looking, you obviously first have to design it. You've got to have a slot, and you book quite far in advance slots just to sort of.
Yeah. It depends. So we obviously we're constantly doing testing and development, and so we can book tests in advance, not knowing necessarily what we're going to use the slot for, but we secure the slots because of the high demand and in fire testing. It's huge demand currently, and that's where if you haven't got slots booked in, then it can take quite a long time to even get a test slot. It can be 12 months sometimes. So but from the design of the test specimen through to installation and then actually fire testing, we generally like to have a cure on the test when we've got sealants or compounds that need some time to cure, and then obviously getting the test report back, and then obviously once we've got that test report, we then get the data classified. So this length of time can be anywhere from 6 to 12, 18 months sometimes. Once we've come up with a idea of something we need to test to actually getting the scope of application. So it is a long process, and we're doing all we can to speed that up where we can. Yeah,
no, it's good. I wanted to sort of highlight that with the audience. So what I would say with anyone out there that's on our website or looking at our stuff, typically when you're seeing our standard details, that's test evidence up to a certain point. So for example, our classification report for our fire bat, which has just been released, is brand new. It's just come out in If you're watching this when it's first released, this video, of course. But that was test evidence up to July 2022. You know, we're now in 2023 and you've continued testing. So if you don't find something in those reports, reach out to our technical team, because Darryl and the rest of the R&D team might have already tested something. We might have something and we can sort of maybe share something, or let you know that speak to us in a couple of months. We've got something coming out there as such. So yeah, no, thank you for joining today, Darryl. Is there sort of any sort of final words that you might want to say, or anything like to the audience at all? Or?
Yeah, absolutely. It is appreciated when we get the feedback coming through. Obviously, some things that come back as feedback, they're not fire testable, as it were. Sometimes people do want things which are unusual applications, and there probably wouldn't be a fire engineering solution for it. So we can't always test everything, but the things that we can engineer something for, we do what we can to create solutions, and that's what we do, is we protect people and property, don't we?
Yeah, no, 100%.
Save lives.
That's the main thing. So, so thank you very much for joining me and Darryl for this episode. If you've enjoyed this, and if you want to know more about fire testing, please send in some questions and comments to our marketing team. The contact info will appear on the screen. And then I'll see if Darryl's free to come back and join me in the future. But from Darryl, thank you very much.